Let's do some examples with explicit functions for differentials. So if we recall, the definition of delta y is the difference in the function value when it's incremented minus the function value at c. So you start at c, and then you take c, you move a little over, you just take the difference in the function values. That's all you're doing. But dy involves derivatives, and you take the derivative of the function at c, and then you multiply it by the differential change. And in this particular case, we're going to choose delta x and dx to be the same value because it's easiest to compare those when they're equal to each other. So for our first problem, we have y equals 3/10 x to the 9th, and our starting point is x equals 1, and our differential change and our incremental change are both 0.1. So let's go ahead and look at that. So in this particular case, f of x is 3/10 x to the 9th. F of c, well, the next thing we know is that c is 1. That's our starting point. C is 1. So f of c is, we just plug in 3/10 times 1 to the 9th, which is 3/10. We also know that delta x is 0.1, so we're given that. So maybe we'll call that 1/10. So that c plus delta x is 11/10, right, when we add those together. So now what we're going to do is we've got everything except for f of c plus delta x. So that's f of 11/10, which is 3/10 times 11/10 to the 9th. It's a pretty big value there. So then what you do is you say delta y is f of c plus delta x minus f of c, which is 3/10, 11/10 to the 9th minus 3/10. Now, if you plug that into a calculator and you calculate that out, you're going to get approximately 0.407. So that's not it's not going to be very clean. You clearly could multiply this all the way out, factor out of 3/10. I mean, you could do this. It would just take you a very long time. Now, if we compare this to dy, we need to get f prime at c. Or first of all, we'll just get f prime of x, which is 27/10 x to the 8th. And f prime at c is 27/10 times 1 to the 8th, which is 2.7, right? Because that's just 1. 27 divided by 10 is 2.7. So if I want to get dy, so this is my first answer, just kind of circling it there. And dy is f prime at c dx. So that's going to be 2.7, 0.1, 0.207, or 27. So in this particular case, it's a pretty bad estimate. And one of the reasons why is because x to the 9th raises so quickly. If you look at if you look at that derivative when x is equal to 1, that 1 to the 8th kind of, it doesn't change much, but if you add a little bit, you get that compound interest problem where 1.0 something raised to a really high power accelerates it. So you're going to end up with a pretty bad estimate across the board there. But it's good to be able to do those and recognize, ooh, this might be not a good candidate for using a differential form, we might have to do, might either have to lower our step size. So instead of using a step size of 1/10, it might have to use 1/100th. But if you use 1/100th, it might turn out a lot more friendly. Anyway, so let's take a look at the next problem over here. Now, I'm gonna use this part of the board because I don't know if I'm gonna run out of room. So in this case, f of x is x to the fourth plus 2. I know that c is -5. I know that delta x is 0.001. So it's a very small step size. In my original problem statement, it was not 0.001, it was 0.01. And so apologies for that. So then we have f of c, which is -5 to the fourth plus 2, which is 25, 125, 625, so that's 627. And then we have f of c plus delta x, which is -4.99 to the fourth plus 2, which, I'll be honest with you, I forgot to calculate. So it is some number, plug it into a calculator, it won't take very long. And if I do delta y, which is f of c plus delta x minus f of c. So if I take 627 and I subtract this number, I'm going to get -4.985. Okay, sorry, my mind blanked for a second while that was true. And the reason that's true is because I was like, this has to be bigger than this, and that's true, but we're subtracting this from this. So there's my answer. Now, to find dy, I need to find, and so that's my answer for delta y. For dy, I take the derivative, I get 4x cubed. I take the derivative at c, I get 4 times -5 cubed, which is -500. So then, if I say dy equals f prime at c dx, that equals -500 times 0.01, which is -5. So what I'm hoping you see here is that using differentials is so much cleaner. Look at that. That was clean, right? Like this is nasty. You wouldn't want to do that by hand. Not only would you not want to do that by hand, even in a computer, it may not be that nice. It's not that big a deal on a computer, but this is clean. This is easy. This is understandable. So differential forms are incredibly powerful. And they provide a very natural intuition for the types of mathematics that we're not only going to do very soon, but the type of mathematics that we'll do as we develop over our study of calculus beyond this course's material to the greater calculus.